Walk past any street corner in Lower Manhattan today and you'll see them. Cast iron columns, usually painted over, maybe holding up a traffic light or serving as a bollard, most people assuming they are simply decorative Victorian infrastructure. Except these are not decorative. They are functional remnants of a system that did something we are told did not exist until recently: distributed electrical power wirelessly across an entire city grid. Not through overhead wires, not through underground cables in the conventional sense. Through the ground itself, using the earth as a conductor, with these iron columns serving as access nodes where businesses and residents could tap into the current. The system operated commercially in New York from the 1880s through the early 1900s. The columns are still there. The patents are in the archives. The municipal records document the installations. And yet most electrical engineering textbooks present wireless power distribution as a modern innovation, maybe mentioning Tesla's experiments as visionary failures, while ignoring that a different approach actually worked and was deployed at scale in multiple American cities. The company that built this system was the Earth Conduction Power Company, though it operated under various subsidiary names depending on the city. The technical principle was straightforward enough that it appeared in multiple patent applications between 1883 and 1895. You establish 2 points of connection with the Earth at different locations, maintain a voltage differential between them, and the ground itself becomes a conductor. Run sufficient current through this circuit, and you create a field gradient in the soil. Plant iron columns into the ground at regular intervals along the gradient, and each column becomes an access point where users can extract current by establishing their own ground connection. The columns were not transmitting through air like radio. They were serving as vertical electrodes in a horizontal current flow through mineralized urban soil. Patent US 324,894, filed by Charles Brush in 1885, describes the basic column installation method. Patent US 338,267, filed by James Denton the same year, details the current collection apparatus that would be attached to each column. These are not speculative drawings, they are engineering specifications for hardware that was manufactured and installed. If you walk down Greenwich Street between Chambers and Warren, there is a cluster of 4 columns, each about 8 inches in diameter, standing at the corners of what used to be a commercial block. 3 of them now hold street signs, 1 supports a traffic signal, all 4 have the characteristic fluted design with a square base plate, and if you check the base plates closely on a dry day, you can still see the mounting holes for the original access panels that would have housed the connection terminals. The New York City Municipal Archives hold installation permits for these specific locations, dated 1887, issued to the Earth Conduction Company, specifying ground electrode columns for electrical distribution. The permits list the depths. These columns are not sitting on the surface, they are driven 12 to 16 feet into the ground, deep enough to reach the water table where soil conductivity increases dramatically. Similar clusters exist on Pearl Street, on Fulton, and throughout the original financial district, where early electrical adoption was concentrated among businesses willing to pay premium rates for lighting. The density of surviving columns in this area is not accidental. This was where the system launched, where the highest current demand existed, and where the ground conditions were most favorable due to centuries of urban development layering conductive materials into the soil. Before you assume this was some limited experiment, consider the scale documented in the archives. The Earth Conduction Company's 1889 annual report, preserved in the New York Public Library's Business Records collection, claims 847 column installations across Lower Manhattan, providing service to 312 commercial customers. The company's 1891 prospectus, attempting to raise capital for expansion, includes a service map showing planned coverage from Battery Park to Houston Street, river to river. The map marks existing columns in blue and proposed installations in red. There are hundreds of blue marks. The company operated a generating station at 35 Liberty Street. The address is listed in contemporary city directories, and the building still stands, though it has been converted to residential use. The generating station had to be massive because the inefficiency of ground conduction meant you needed enormous current to deliver useful power at the endpoints. We are talking generators capable of producing thousands of amperes at relatively low voltage, which required significant coal-burning capacity and cooling infrastructure. The 1890 engineering report, submitted to the city's Board of Electrical Control, describes a facility with 4 steam engines, each rated at 500 horsepower, driving generators that could collectively output 12,000 amperes at 110 volts. That is over a megawatt of generating capacity dedicated specifically to ground conduction distribution. Here's what makes this technically fascinating. The system actually worked better in urban environments than it would have in rural areas, which is counterintuitive until you understand the soil conditions. Manhattan bedrock is schist, which is a terrible conductor, but Manhattan fill, the layers of soil, ash, construction debris and decomposed organic matter that covered the bedrock as the city developed, is a different story. It is full of mineral salts from centuries of human habitation, saturated with groundwater and laced with iron fragments and other conductive debris. Run current through wet, mineralized urban fill, and you get conductivity several orders of magnitude better than through rural topsoil. The Earth Conduction Company's technical literature specifically marketed this advantage, arguing that their system was particularly suited to densely built cities where the very density created superior ground conductivity. They were not entirely wrong. The columns installed in drier, less built-up areas like the edges of Central Park showed much higher resistance and lower current delivery. The system was essentially parasitic on urbanization itself. The 1888 technical manual produced for installers, preserved in the Library of Congress, includes soil conductivity tables for different Manhattan neighborhoods, showing measured resistance values that varied by more than a factor of 20 depending on location. The financial district, with its layers of construction fill and proximity to the water table, showed resistances as low as 8 ohms per 100 feet. Areas north of 14th Street, where bedrock was closer to the surface and soil was less mineralized, showed resistances exceeding 150 ohms per 100 feet, making them essentially unviable for the system. User experience was documented in trade publications from the period. The Electrical World Journal from November 1888 describes a visit to a Greenwich Street tobacco shop that received power via a ground conduction column. The shopkeeper had a connection box mounted on the exterior wall next to the column. Inside the box was a knife switch, a fuse, and a terminal strip. A cable ran from the terminal strip into the shop to power 6 incandescent lamps. The shopkeeper paid monthly based on the number of lamps connected, not on metered usage, because the technology to measure current draw through a ground conduction system apparently did not exist or was not economically viable. The rates were high, about $3 per lamp per month, compared to roughly $1 per lamp for customers on conventional wired systems. But in locations where building owners prohibited overhead wires or where installing underground conduit was prohibitively expensive, ground conduction offered the only practical option besides generating power on site with a private dynamo. The article notes that the tobacco shop owner had previously used gas lighting at a cost of about $2 per fixture per month when fuel and maintenance were factored in, so the electrical service, despite its premium pricing, represented only a marginal increase in lighting costs while providing superior illumination. Other customers included a printing shop on Pearl Street that ran a small electric motor for a bindery machine, a jeweler on Fulton Street who used the power for precision lighting at workbenches, and a tavern on Stone Street that operated an early electric ventilation fan. Each of these installations is documented in the company's customer ledgers from 1889 to 1892. Those ledgers survived in the archives because they became evidence in the bankruptcy proceedings when the company collapsed. The columns themselves were manufactured by multiple foundries. The Architectural Ironworks Company in Brooklyn produced many of them according to specifications found in their 1886 catalogue, which is preserved in the Smithsonian's Trade Catalogue collection. The catalogue listing describes ground electrode columns for electrical conduction available in heights from 8 to 14 feet, with diameters from 6 to 10 inches, cast in grey iron with an optional bronze finish. The base plates were standardized at 18 inches square to provide stability, and each column was shipped with a threaded cap at the top that could be removed to access the internal connection rod. That internal rod ran the full length of the column and extended another 4 to 8 feet below ground, terminating in a bell-shaped electrode that increased surface area contact with the soil. The installation procedure specified in Patent US 341772 involved drilling a pilot hole with a steam-powered auger, driving the column and electrode assembly into place with a pile driver, backfilling around the base plate with concrete, and then testing the ground resistance before connecting the column to the distribution circuit. The installation cost documented in the company's 1888 expense reports averaged $42 per column, including materials and labor, which was substantial but less than the cost of running underground conduit for the equivalent distance. The columns were designed to be maintenance-free once installed, with the assumption that the cast iron would resist corrosion for decades. This assumption turned out to be largely correct. The columns that remain today, over a century later, show remarkably little deterioration beyond surface rust, though some have developed cracks from ground settling or impact damage over the years. Why did this system fail commercially despite being technically operational? The conventional narrative points to Tesla's alternating current distribution system winning out, but the timeline does not line up because Tesla's polyphase system was not widely deployed in New York until the mid-1890s. The important issues were efficiency and safety. The electrical losses in ground conduction were catastrophic by modern standards. For every kilowatt delivered to a customer, the generating station had to produce 10 to 15 kilowatts, depending on soil conditions and distance. Most of that power was dissipated as heat in the ground. That meant fuel costs were enormous, making the system economically marginal, even at premium pricing. And then there were the stray current effects. The New York Board of Electrical Control received dozens of complaints between 1888 and 1892 about tingling sensations when people touched iron railings, unexpected corrosion of underground pipes, and interference with telephone circuits. The ground was not a neutral conductor, it was a complex electrochemical environment, and pumping thousands of amperes through it created all sorts of unintended consequences. Patent US 401883, filed in 1889 by the engineer Edison, describes a mitigation system for reducing stray ground currents from electrical distribution. It was clearly developed in response to problems the Earth Conduction Company was creating. The interference with telephone service became particularly contentious because telephone companies were simultaneously trying to expand underground cable networks. Ground currents from the power distribution system induced noise and crosstalk that made telephone service unreliable. The Western Union Telegraph Company filed a formal complaint with the city in 1891, demanding that ground conduction power distribution be banned as a public nuisance. The complaint included affidavits from telegraph operators describing how messages became garbled whenever the Earth Conduction Company's generators were running at full capacity. By 1895, the company had largely ceased new installations and was focusing on maintaining service to existing customers. By 1902, most of those customers had switched to conventional wired service as it became available. The generating station was decommissioned in 1905. 5. But here is the remarkable part. Nobody bothered to remove the columns. Why would they? They were cast iron, driven deep into the ground. Removing them would require excavation equipment and would tear up the streets. It was much easier to simply disconnect them from the dead distribution system, seal the access panels and leave them in place. Some were repurposed almost immediately as mounting points for early streetlights. Others just stood there. As decades passed and institutional memory faded, the columns became invisible, familiar enough that nobody questioned them, obscure enough that their original purpose was forgotten. Today, urban planners see them as historic street furniture, maybe dating from the gas lamp era, vaguely decorative, and certainly not worth the expense of removal. The city's Department of Transportation actually maintains an inventory of these columns, categorizing them as historic iron street posts with installation dates listed as unknown, presumed 1880s to 1900s. The inventory does not mention electrical distribution. It classifies them purely as architectural elements. When street reconstruction projects require moving or removing these columns, the work is sometimes contracted to preservation specialists who treat them as fragile historic artifacts, unaware that they are handling components of an electrical distribution system that was operating at industrial power levels. The evidence for all of this is not hidden or suppressed. It is sitting in public archives, waiting for anyone curious enough to look. The New York City Municipal Archives holds the original installation permits in the Department of Public Works records filed by date under electrical infrastructure. The Patent Office holds the complete technical specifications with drawings that show cross-sections of the column installations. The New York Public Library has trade journal articles describing the system in operation. The Smithsonian has manufacturer catalogs that list the columns as standard products. You can physically visit the column locations today and verify that they match the addresses in the 1889 service map. This is not speculative history or conspiracy theory. It is documented infrastructure that contradicts the simplified story we tell about how electrical distribution developed. We act as if the path from Edison's first central station to modern alternating current grids was inevitable and linear. But the archival record shows something messier, multiple competing systems, some of which worked well enough to be deployed commercially but failed for economic or political reasons rather than technical impossibility. Similar ground conduction systems operated in Philadelphia, where the Telluric Power Company installed columns throughout the industrial districts along the Delaware River waterfront. The Philadelphia City Archives have permits for 423 column installations from 1887 to 1893, concentrated in areas where factories needed power but were located in buildings where landlords refused to allow external wiring. The columns there had a different design, shorter and thicker, only 6 feet above ground but with electrodes extending 20 feet down to reach the clay layers beneath the river fill. Some of these columns are still visible along Delaware Avenue, though most have been painted over so many times they are unrecognizable. The Philadelphia system actually had some technical advantages over the New York installation. The clay soil provided more uniform conductivity than Manhattan's variable fill, which meant more predictable power delivery and fewer complaints about performance variation. The Telluric Power Company's 1890 promotional literature boasted that their system could deliver consistent current regardless of weather conditions, unlike overhead wire systems that experienced voltage drops during storms. What the promotional literature did not mention was that the clay soil also retained moisture longer, which meant higher sustained ground currents and accelerated corrosion of underground metal infrastructure belonging to other utilities. The Philadelphia Water Department filed a complaint in 1892, claiming that the ground conduction system had caused premature failure of iron water mains in the service area, requiring replacement of over 2 miles of pipe at considerable expense. The Telluric Power Company disputed the claim, arguing that the water mains were already corroded from other causes but the controversy damaged the company's reputation and made expansion difficult. In Chicago, a ground conduction system operated in the Stockyards district, where the blood-soaked soil apparently provided exceptional conductivity. The Chicago system used wooden poles instead of iron columns, which seems surprising from a modern perspective, but the poles were impregnated with metallic salts and essentially functioned as vertical electrodes. None of the Chicago poles survived. They rotted out by the 1920s, but the installation records are preserved in the Chicago History Museum, and they describe a distribution network covering over 40 acres of the Stockyards complex. The system there was designed specifically for the unique conditions of the meatpacking industry. The slaughterhouses needed power for electric lighting to extend working hours and for electric motors to drive sausage stuffers, meat grinders, and refrigeration compressors. The buildings were constantly being hosed down with water mixed with blood and offal, creating an environment where conventional electrical wiring presented serious shock hazards. The ground conduction system offered a solution. Power could be accessed via terminals mounted on exterior walls, keeping all the wiring outside the wet processing areas. The Stockyards installation was documented in a case study published in Western Electrician magazine in 1891, which described how Armour and Company, one of the major meat packers, had equipped 12 processing buildings with ground conduction power service. The article noted that the system worked remarkably well in the Stockyards, despite the unconventional pole design, with soil conductivity so high that power could be delivered at distances up to 800 feet from the generating station with acceptable voltage drop. The exceptional conductivity apparently resulted from the combination of organic decomposition products, mineral salts from curing processes, and constant moisture saturation from industrial runoff. The question is not why ground conduction failed. The efficiency problems were insurmountable with the technology of that era. The question is why this technological path has been so thoroughly forgotten. Part of the answer is institutional. The societies and companies that promoted ground conduction went bankrupt and left no successor organizations to preserve their history. The Institute of Electrical and Electronics Engineers, which maintains the profession's historical records, was formed by the merger of organizations that had been dominated by advocates of wired distribution systems. Ground conduction was the losing side, and losing sides do not get much archival attention. But there is also a deeper issue about how we construct technological narratives. We want the history of innovation to be a story of steady progress toward the systems we use today, with failed alternatives dismissed as dead ends rather than examined as legitimate engineering solutions that happen to lose economic competitions. Ground conduction does not fit the narrative that wireless power distribution is a modern innovation, so it gets omitted from textbooks. When ground conduction appears in historical accounts at all, it is usually mentioned briefly as one of the many failed systems from the chaotic early years of electrification, grouped together with other abandoned approaches without any serious examination of how they actually worked or why they failed. The technical details get lost, the physical evidence gets misidentified, and within a few generations the entire episode becomes invisible, even though the infrastructure remains in plain sight. What is most striking is how this pattern of forgetting repeats across different technologies. Consider the compressed air distribution systems that provided power to thousands of machines in New York and Paris through the 1890s, using similar street-level access points. Consider the vacuum systems that provided suction power for elevators and industrial equipment through underground lines. Consider the hydraulic power networks in London and Melbourne that used pressurized water to drive machinery across entire districts. All of these were large-scale, commercially successful infrastructure systems that operated for decades, left physical remnants that still exist, and then vanished from collective memory to the point where modern engineers are often shocked to learn they were real. We tell ourselves that technology progresses linearly from simple to complex, from local to networked, from inefficient to optimized. But the archival record shows something different. The landscape is littered with sophisticated networked systems that worked well enough to be profitable for a time, then became obsolete for reasons that had more to do with economics and standardization than with inherent technical limitations. The cast iron columns scattered across Lower Manhattan are not decorative relics of a simpler age. They are the physical proof that our ancestors were solving distribution problems with methods we have forgotten were possible, and that the technological present is built as much on selective amnesia as it is on cumulative progress.